Hello friends, welcome to my lecture on continuous probability distribution. Let S be a sample space which is an interval of the real line or have points defined in a continuum. For such sample spaces, we define the random variable in such a way that they take all values in an interval of values. For example, we can define the random variable to denote the life of an electron tube, service time required to complete a job, heights of individuals. Okay? They all come under continuous random variables. So, such random variables are all continuous random variables. Now, a continuous random variable is a random variable defined on a sample space S, okay, and which takes all values in an interval with probability p defined for events of S. Continuous random variable x can be specified by its cumulative distribution function. Cumulative distribution function is the probability that we denote it by f x x, x is the continuous random variable, okay. F denotes the cumulative distribution function. So, f x x is probability that x takes the value less than or equal to x, where x belongs to the interval minus infinity to infinity. Now, this f x x is monotonically non-decreasing function of x, okay, because you can find f x x 2 minus f x x 1, this will come out to be probability that x 1 is less than or equal to x less than or equal to x 2. f x x 2 is equal to probability that x is less than or equal to x 2, and f x x 1 is equal to probability that x is less than or equal to x 1. Okay. So, f x x 2 minus f x x 1, okay, f x x 2 minus f x x 1, okay, is probability that x is less than or equal to x 2 minus probability that x is less than or equal to x 1. Okay. So, this is probability that x 1 is less than x less than or equal to x 2. Okay. Since probability is a non-negative function, this is greater than or equal to 0. Okay. So, whenever x 1 is less than x, so here we are assuming that x 1 is less than x 2. So, when x 1 is less than x 2, f x x 2 minus f x x 1 is greater than or equal to 0, that is f x x 1 is less than or equal to f x x 2. So, f x x is a monotonically non-decreasing function of x. Now, limit x tends to minus infinity, limit x tends to minus infinity, f x x is limit x tends to minus infinity, probability that x is less than or equal to x, that is equal to 0. Okay. Because probability that x is less than or equal to x when x tends to minus infinity, okay, will be equal to 0, and when limit because this is nothing but this is probability x less than or equal to x, this is nothing but minus integral over minus infinity to x f x x dx, as we shall see later on. We shall see later on that this is f x x is nothing but integral over minus infinity to x f x x dx. So, when x tends to minus infinity, f x x tends to 0. So, limit x tends to minus infinity, p x less than or equal to x is 0, and here limit x tends to f x x, that is limit x tends to infinity, probability that x is less than or equal to x will be equal to 1, okay, because it will be then the total probability will be equal to 1. f x x is right continuous, okay. Right continuous means limit h tends to 0 plus, okay, f x x plus h is equal to f x x. Okay. So, it is right continuous. Now, for a continuous random variable, we define a function corresponding to the probability distribution of a discrete random variable. For a continuous random variable, we define a function corresponding to the probability distribution of a discrete random variable. It is denoted by f x x. So, this is known as the probability density function for the random variable, continuous random variable x, and it is defined as the derivative of the distribution function f x x. So, this probability density function f x x is defined as the derivative of the distribution function f x x at x. Okay. So, the probability density function f x x of a continuous random variable is defined as d over dx of f x x, okay, where x varies over minus infinity to infinity. From this equation one can see that f x x is integral over minus infinity to x f x t dt. Okay. So, you can see since f x x is a monotonically increasing function, okay, its derivative must be non-negative. Okay. This follows because f x x is monotonically increasing. F x x is monotonically increasing. So, its derivative is non-negative. So, f x x is greater than or equal to 0, and furthermore limit x tends to infinity, f x x is equal to 1. Okay. We have assumed that limit x tends to infinity f x x is equal to 1. Okay. So, from there, okay, this will be equal to integral over minus infinity to infinity f x t dt. Okay. So, when x tends to infinity, f x x tends to integral over minus infinity to infinity f x t dt, and we have limit x tends to infinity f x x equal to 1. So, integral over minus infinity to infinity f x x dx equal to 1. Now, we can note that f x x itself is not a probability, it can be greater than 1 for some values of x. Okay. The integral of f x x over minus infinity to infinity is 1. Okay. So, consider the distribution function. So, this is our distribution function, cumulative distribution function f x x equal to 0 when x is less than 0, 2 x 0 for 0 less than or equal to x less than or equal to half, and 1 when x is greater than half. Okay. So, let us find its derivative d over dx of f x x. By our definition, this is f x x, probability density function. So, f x x will be equal to 0 when x is less than 0. Okay. Derivative of 0 is 0, and then 0 less than or equal to x less than or equal to half. Okay. So, here the derivative will be 2, derivative of 2 x will be 2, and it will be over the interval 0 less than x less than half. Why? Because if you draw the graph of this cumulative distribution function, so it is 0 for x less than 0. Okay. 0 for x less than 0, and then 0 to half it is 2 x, it is given by 2 x. So, that means it is a straight line, this is half here. So, it is like this. Okay. At x equal to 2 it is 1. So, this is 1. Okay. So, we have this, okay, and then x greater than half it is 1. Okay. So, like this. Okay. Now, you can see at x equal to 0 and at x equal to half it is not differentiable, because the left hand derivative is 0, right hand derivative is 2. Okay. So, it is not differentiable at 0, it is not differentiable at half. Okay. So, f x x is not differentiable although it is continuous throughout over minus infinity to infinity, but is not differentiable at x equal to 0 and x equal to half, elsewhere it is differentiable. So, in the interval open interval 0 less than x less than half, the derivative of f x x is equal to 2, and when x is greater than half its derivative is 0. So, you can see the probability density function is taking value 0 over the interval minus infinity to 0. So, that means here up to this it is 0 everywhere, and then it is 2 over 0 half interval. Okay. So, it is 0 half over 0 half it is 2, okay, and this is f x x, this is f x x cumulative distribution function. Okay. And now, here then it takes value 0. So, from here onwards it takes value 0. Okay. So, this f x x can take value other than 1, it can take value greater than 1. Okay. Here it is taking value 2. Okay. But the integral of f x x over minus infinity to infinity must be equal to 1, that you can see. So, f x x dx, this will be equal to integral, because over 0 minus infinity 0 it is 0, over half to infinity it is 0, it is non-zero over the interval 0 half. So, this is 0 to half and 2 dx, this is equal to 2 into 1 by 2, which is equal to 1. Okay. And moreover, it is non-negative, f x x is greater than or equal to 0 for all x. So, it is probability density function. Now, let us go to so here I have explained clearly f x x is greater than 1 for 0 less than x less than half. It is discontinuous at x equal to 0, you can see it is discontinuous at x equal to 0 and also discontinuous at x equal to half. In the case of a continuous random variable x, note that the probability that x takes exactly the specific value x is equal to 0. That means, probability that x takes the value a, okay, or x is equal to 0. Okay. So, since p x equal to a equal to p x equal to b equal to 0 for a continuous random variable, all the 4 expressions, probability of a less than x less than b, probability a less than or equal to x less than b, a less than x less than or equal to b, probability of a less than or equal to x less than or equal to b are all equal. Okay. Now, probability of a less than x less than or equal to b is integral over a to b f x dt f x t dt, because probability a less than x less than or equal to b, this is equal to probability that x is less than or equal to b minus probability that x is less than or equal to a. Okay. So, this is f x b minus f x a, we can say. Okay. And this is equal to integral over minus infinity to b f x x dx minus integral over minus infinity to a f x x dx. Okay. Since a is less than b, okay, this is equal to integral over minus integral over a to b f x x dx. Okay. So, f x t dt we can write. Okay. So, it is the area under the graph of f x x function, okay, from over the interval a to b. So, it is the area under the graph of f x x between x equal to a and x equal to b, okay, as shown in this figure. Now, let us consider the following function f x x equal to 4 x over the interval 0 less than or equal to x less than or equal to half, 4 into 1 minus x 1 by 2 less than or equal to x less than or equal to 1 and 0 otherwise. So, we have drawn the graph here. Over the interval 0 1 it is given by this, over the interval 0 to half it is given by the straight line by equal to f x x equal to 4 x, okay. Over the interval half to 1 it is given by this straight line 4 into 1 minus x. So, this is 4 x f x x equal to 4 x and this is f x x equal to 4 times 1 minus x. Okay. Now, we have to show that it is a probability density function. First of all, let us note that f x x is greater than or equal to 0 for all x belonging to minus infinity to infinity. Okay. The graph of f x x lies above the x axis. On the negative side of x axis it is 0 everywhere, on the positive side of x axis after 1, okay, after 1 it is 0 and over 0 to 1 it takes non-negative values. So, it is greater than or equal to 0 for all x. Now, it is a probability density function provided we prove that integral over minus infinity to infinity f x x dx equal to 0 is equal to 1. Okay. So, over minus infinity to 0 it is 0, over 1 to infinity it is 0. So, we can write it as integral over 0 to 1 f x x dx, which is equal to integral over 0 to half, over 0 to half it is 4 x and then over half to 1 it is 4 times 1 minus x. Okay. So, we can integrate this 4 times x square by 2 0 half plus 4 times x minus x square by 2 half to 1. we can substitute the limit and we shall see that this it comes out to be 1. Otherwise also we can see from the geometry also we can find the integral over minus infinity to infinity f x dx. This is integral over 0 to 1 f x dx, that means the area bounded by this triangle. Okay. Integral over 0 to 1 f x x dx is the area bounded by the triangle, and this area is how much? 1 by 2 into base into height, area of the triangle. So, this will be 1 by 2, base is equal to 1 and height is at x equal to half. Okay. At x equal to half, we can see it is f x x equal to 4 x. So, at x equal to half, the height is 2. Okay. So, this is equal to 1. Okay. So, area of the triangle is integral over 0 to 1 f x x dx, which is equal to integral over minus infinity to infinity f x x dx. So, f x x is a probability density function. Okay. Now, let us find its cumulative distribution function. So, cumulative distribution function is f x x, and it is given by integral over minus infinity to x f x x dx. Okay. So, first we consider the case when x is less than 0. When x is less than 0, f x x is 0. So, this probability density function assumes value 0. So, cumulative distribution function is also 0. Okay. So, f x x is equal to 0 if x is less than 0. Okay. Then let us consider the case let us consider the case when 0 is less than or equal to x less than half. Okay. So, we consider the case 0, suppose x is greater than or equal to 0, but less than half. Okay. So, we can assume this is equal to, in fact also r of x equal to 1 by 2 also we can take. So, we will have integral over minus infinity to x. So, that means minus infinity to 0 f x x dx plus integral over 0 to half f x x dx. Okay. So, this is equal to 0 because over minus infinity to 0 f x x is 0, and then 0 to half it is given by 4 x dx, 4 x. Okay. So, this is 2 x square. So, 0 to it is x. Okay, let not half. So, we can write it as 0 to x, not half. Okay. So, this will be 2 x square 0 to x, that is 2 x square. Okay. Then f x x equal to minus infinity to x f x dx. Let us find f x x when x is greater than half and less than or equal to 1. So, 1 by 2 less than x less than or equal to 1. Okay. Then we have minus infinity to 0, 0 to half, and then half to x. Okay. Half to x f x x dx. So, we shall have here integral over minus infinity to 0 f x x dx will be 0 because the function f x x is 0, then 0 to half f x x dx, 0 to half f x x is 4 x. So, 4 x dx, then half to 1, half to x, f x x is 4 times 1 minus x, 4 times 1 minus x. Okay. So, we will get this as this is 2 x square 0 to half, and here we will get 4 times x minus x square by 2 half to x. Okay. So, this is 2 into 1 by 4, 2 into 1 by 4 plus 4 times x minus x square by 2 minus 4 times 1 by 2 minus 1 by 2 square, that is 1 by 4 by 2 by 1 by 8. Okay. So, how much it will be? This is equal to 1 by 2, okay, plus 4x minus 2x square, and what we get here 1 by 2 minus 1 by 8 is or we can multiply by 4. So, minus 2, okay, and plus 1 by 2. So, what do we get? This is half is 1 minus 1. So, 4x minus 2x square minus 1. Okay. So, when x lies in this interval, okay, x lies in this interval, f x x is equal to 4x minus 2x square minus 1. Okay. So, 4x f x x equal to 4x minus 2x square minus 1, provided half is less than x less than or equal to 1, and when x is greater than 1. Okay. Now, let us consider the case when x is greater than 1. Okay. Then f x x equal to integral over minus infinity to x f x x dx is equal to integral over minus infinity to 0, okay, plus integral over 0 to half plus integral over half to 1, okay, plus integral over 1 to x f x t dt. Okay. So, this is equal to integral over minus half to 0, it is 0, then integral over 0 to half plus integral over half to 1 f x t we have found is equal to 1. So, we have 1 plus integral over 1 to x, okay, integral over 0 to half plus integral over half to 1 this is integral over 0 to half plus integral half to 1 f x t dt is equal to 1, and integral over 1 to x f x t dt is equal to 0, because that is 0. Okay. F x t is 0 over the for x greater than 1. So, f x x equal to 1 when x is greater than 1. So, thus we have f x x equal to 0 when x is less than 0, and we have f x x equal to 2 x square when x is lying between 0 and half, and then we have 4x minus 2x square minus 1 when 1 is by 2 is less than x less than or equal to 1, and the 1 when x is greater than 1. So, this is how we find the cumulative distribution function. Okay. Now, we go to the definition of expectation and variance. Let x be a random variable with probability density function f x x. If g is a function of x, then the expectation of g x denoted by E g x is defined as E g x equal to integral over minus infinity to infinity g x f x x dx. The mean of f x are equivalently the expectation of x is given by integral over E x equal to integral over minus infinity to infinity x f x x dx, and expectation of x square is similarly defined integral over minus infinity to infinity x square f x x dx. Now, variance of x we know variance of x is expectation of x square minus expectation of x whole square. So, this is how we can determine variance of x once we have the values of E x and E x square. Now, let us consider this question: the demand x for a certain community is a random variable and has the following probability density function f x x equal to 1 by 10, 70 less than x less than 80 and 0 otherwise. We can find here we can see that integral over minus infinity to infinity f x x is equal to integral over 70 to 80 1 by 10 dx. Okay, this is equal to 1, okay, and also that f x x is greater than or equal to 0. So, that we can see here it takes non-negative values. Okay. So, f x x is a probability density function. We can find mean here. So, expectation of x equal to integral over minus infinity to infinity x into f x x dx. So, this will be integral over 70 to 80 x times 1 by 10 dx, and this will be equal to 1 by 10 times x square by 2, 70 to 80. So, we can find here this is 1 by 20 and then we have 80 square minus 70 square. Okay. So, this is equal to 1 by 20 times this is 80 square. So, 80 square minus 70 square is 80 minus 70, that is 10 into 80 plus 70, that is 150. Okay. So, we have 75. Okay. So, expectation is 75, expectation of x square if you find, this will be equal to integral over minus infinity to infinity x square f x x dx, and this will be equal to integral over 70 to 80 1 by 10 that is f x x into x square dx. So, this is 1 by 10 x cube by 3, okay, 70 to 80. So, this is 1 by 10 80 cube minus 70 cube divided by 3. Okay. So, this is 1 by 30, then we can factorize this. So, 80 a cube minus b cube is a minus b, that is 80 minus 70 is 10 into a square. So, 80 square plus b square means 70 square plus a b means 80 into 70. Okay. So, this will give you equal to, this is 80 square is 6400 plus 4900 plus 80 into 7 5600 divided by 3. Okay. So, this will come out to be 0 0 4 9 13 13 and 6 is 19, and then 7 4 11 11 5 16. Okay. So, this is E x square. Now, once we have E x square, we can subtract from E x square E x whole square to get the variance of x. So, variance of x will be equal to E x square, that is 16900 divided by 3 minus 75 whole square, and we get the variance of x. Okay. So, we can calculate the variance of x here, and that from that variance of x we can find the value of standard deviation also. Okay. Now, let us go to uniform distribution. The uniform distribution is one of the simplest probability distributions. It is a continuous distribution. This means that it takes values within a specified range, that is between 0 and 1. Okay. So, let us take a and b to be any two real numbers such that a is less than b. Okay. As a random variable, x is called uniformly distributed between a and b if its probability density function is given by 1 over b minus a less than x less than b and 0 otherwise. We can draw its graph. Suppose a is less than 0 less than b, then the graph of the probability density function of the normal uniform distribution is given by this. Okay. A between a to b, it takes values 1 over b minus a, elsewhere it takes values 0. The area under the graph of f x you can see is 1 over b minus a into b minus a, so equal to 1. The area bounded by the rectangle is 1. Okay. Now, the distribution function we can see here, the distribution function f x x. We know it is its definition is minus infinity to x f x x dx, integral over minus infinity to x f x x dx, and this will be equal to 0 if x is less than a. Okay. If x is less than a, okay. So, this will be 0 if a is less than or equal to x less than or equal to b. So, this will be equal to integral over a to x f x x dx, because over minus infinity to a f x x dx f x x is 0. So, this will be equal to integral over a to x, okay, 1 over b minus a dx, and this will be equal to x minus a divided by b minus a. Okay. So, over the interval a less than or equal to x less than or equal to b, it is x minus a over b minus a, and when x is greater than b, okay, f x x equal to 1. Okay. So, we have this cumulative distribution function, and we can see its graph. When x is less than a, it is 0. When x lies between a and b, it is given by the straight line x minus a over b minus a. So, this is f x x equal to x minus a over b minus a, and the here f x x is equal to 1. This is okay. So, okay. So, this is the graph of cumulative distribution function of a uniform distribution. Now, you can see the shape of the curve in this one is rectangular. Okay. This is the curve is here it is rectangular shape. So, that is why rectangular this uniform distribution is also called a rectangular distribution. Okay. It is called uniform distribution because the PDF is constant over the interval a b, the interval in which the random variable takes its values. We apply this distribution if the random variable is equally likely to take any of the possible values in an interval. E x is equal to a plus b by 2, as we have just now calculated E x in a in this case of this example. In the case of this example, similarly we can calculate the E x for the case of the uniform distribution. So, E x will be equal to integral over minus infinity to infinity x times f x x dx. So, this will be equal to integral over a to b, okay, x times f x x integral over a to b, f x x is 1 over b minus a dx. Okay. So, this will be equal to 1 over b minus a x square by 2 a to b, and this will be b square minus a square divided by 2 times b minus a. So, this is b plus a by 2. Similarly, if we calculate E x square will be integral over minus infinity to infinity x square f x x dx. This is equal to integral over a to b x square 1 over b minus a dx, and this will be equal to 1 over b minus a x cube by 3. So, it is a to b. So, this is 1 over b minus a b cube minus a cube divided by 3. So, this is b square plus a square plus a b divided by 3. Okay. We get this formula, and then we can calculate variance of x from this formula, E x minus E x whole square. Okay. So, so we can apply this formula, and we will get variance of x to be equal to a minus b whole square divided by 12. Okay. Now, we can consider the example A, okay, this example, this one. Okay. So, we can consider in this example we have been given the values of a and b, a is 70, b is 80. Okay. So, we can put these values a equal to 70, b equal to 80, then E x is 75, and when you put here a equal to 70, b equal to 80, then 80 minus 70, 10, 100 square by 12. So, variance of x is equal to E x equal to 10 plus 70 70 plus 80 by 2, meaning that it is 75. It is 75, and variance of x will be equal to at 70 minus 80, that is 100 square divided by 12. So, 100 by 12, which means that it is 25 by 3. Okay. So, that is the variance of x. Okay. Now, let us go to this example. Suppose a man is about to take an elevator to go to his flat in a building. Once he calls the elevator, suppose it takes between 0 and 40 seconds to arrive to him. Okay. Assuming that the elevator arrives uniformly between 0 and 40 seconds after the man presses the button, determine the probability that the elevator takes less than 15 seconds to arrive to the man. Okay. So, this is uniform distribution here. So, we have to find the probability that x is less than or equal to 15. Okay. The f x x is given by 1 over b minus a. So, 1 over b minus a means 1 over 40 minus 0. So, 1 over 40 when 0 is less than x less than 40, okay, and 0 otherwise. Okay. 0 less than x less than or equal to 40, it is 140, 1 by 40 and 0 otherwise. So, this will be equal to integral over minus infinity to 15, okay, f x x dx. So, this will be equal to integral over 0 to 15 f x x, that is 1 by 40 dx. Okay. So, 15 by 40, which means that 3 by 8. Okay. Also find the expected time of arrival and variance. So, expectation of x will be equal to, as we have just now seen, expectation of x is equal to a plus b by 2. A plus b by 2 means 0 plus 40 by 2. Okay. 0 plus 40 by 2, that means 20. And variance of x we have just now seen, variance of x is equal to a minus b whole square by 12. Okay. So, a is 0, b is 40. So, 40 square divided by 12. So, this means 1600 divided by 12. Okay. So, this is 400 divided by 3. Okay. So, that is the variance. Now, let us suppose in a quiz there are 30 participants, a question is given to all 30 participants and the time allowed is 25 seconds. Find the probability of participants who respond within 6 seconds. Okay. So, we have to find the probability that x is less than or equal to 6. Okay. So, this is integral over minus infinity to 6, okay, f x x dx. Okay. So, this is integral over 0 to 6, okay, f x x is 1 over 25, okay, dx. So, this is 6 by 25. Okay. So, here the f x x is given by 1 over b minus a, that is 25, okay, 0 less than x, 0 less than x less than 25 and 0 elsewhere. The number of participants, okay, find the number of participants who respond within 6 seconds. So, number of participants equal to 30 into 6 by 25, that means 36 by 5. So, that is approximately 7. So, number of participants who respond within 6 seconds is 7. Okay. Now, let us see metro trains run on a certain line every half hour between midnight and 6 in the morning. What is the probability that a man entering the station at a random time during this period will have to wait at least 20 minutes. So, let us say let x denote the waiting time, let x denote the waiting time for the train, metro train. Okay. Let us x denote the waiting time of the man. Let x denote the waiting time of the man for the metro train. Okay. Then probability that he has to wait at least 20 minutes. So, x varies between 20 less than or equal to x less than or equal to 30, because every half hour there is a train. So, integral over 20 to 30, okay, f x x dx. Okay. Now, f x x is equal to 1 over b minus a. So, 1 over 30 minus 0, 30, because every half hour there is a train. So, 30 minus 0, 0 less than x less than 30 and 0 elsewhere. So, this will be 20 to 30, 1 by 30 dx, and it will be equal to 10 by 30, that means 1 by 3. So, probability that the man will have to wait at least 20 minutes is 1 by 3. So, this is where I would like to end my lecture. Thank you very much for your attention.